Imagine standing in the middle of a vast field at night, gazing up at the sky. The stars glitter like scattered jewels across a dark velvet canvas. Since ancient times, humans have looked at that sight and wondered, how vast is the universe? Where did it come from? And where is it going? For most of human history, those questions had no definitive answers. We imagined the heavens as a fixed dome, with celestial objects moving in eternal cycles. Only in the 20th century, with the advent of the Big Bang Theory, did we begin to understand the universe is not static, it had a beginning. And ever since, it has been expanding. This idea was radical, a universe that grows over time, instead of standing still, ran against centuries of intuition and tradition. But evidence from Edwin Hubble's discovery of galactic redshifts was undeniable. The farther away a galaxy is, the faster it recedes. The universe is like an inflating balloon, its surface stretching outward, galaxies embedded like tiny dots carried along with the expansion. For decades, scientists debated the ultimate fate of this expansion. Would gravity, pulling on all matter in the cosmos, eventually slow it down and perhaps even reverse it, leading to a catastrophic Big Crunch? Or was there too little matter, meaning the universe would expand forever, but gradually slowing as it cooled into darkness? The story seemed set within these familiar possibilities, until the late 1990s. When international teams observed Type Ia supernovae in distant galaxies, they uncovered something no one expected. The universe is not slowing down at all. In fact, it is accelerating. Pause for a moment to grasp the shock. The universe we thought was slowing, like a ball tossed into the air, was instead racing faster with time. This discovery shook the foundations of cosmology so profoundly that three scientists, Saul Perlmutter, Brian Schmidt, and Adam Rees, were awarded the 2011 Nobel Prize in Physics. This revelation forced humanity to admit that something unseen, something we had never accounted for, was at work, permeating the cosmos and driving galaxies apart ever faster. We gave it a simple yet haunting name: dark energy. When we speak of dark energy, picture an invisible architect working backstage, shaping the grand stage of the cosmos. It emits no light, absorbs no radiation, cannot be captured in any laboratory. Yet its fingerprints are everywhere. It is the silent hand stretching the fabric of space itself. Albert Einstein once introduced the cosmological constant while developing his theory of general relativity. His equations predicted a dynamic universe, either expanding or contracting, but because scientists of his time believed in a static cosmos, he added a constant to counterbalance gravity. Later, when Hubble proved the universe was expanding, Einstein famously called it the biggest blunder of my life. But history has a sense of irony. That very constant may hold the key to explaining dark energy. Perhaps the vacuum itself has energy, a built-in push embedded in the structure of spacetime. Yet this is only one possibility. Some theorists suggest dark energy isn't constant but dynamic, changing over time, a concept known as quintessence. Others propose something even bolder. Perhaps Einstein's theory itself is incomplete, and the laws of gravity need to be rewritten. What we do know comes from numbers. Today, precision measurements from satellites like Planck reveal the startling composition of the cosmos: about 68% dark energy, 27% dark matter, another invisible ingredient known only through its gravitational effects, and just 5% ordinary matter. The atoms that make up stars, planets, trees, oceans, and ourselves. Think about that. Everything we have ever touched, seen, or measured, all of human history, every galaxy we marvel at, belongs to a mere sliver of reality. The vast majority of the universe lies in two mysterious shadows. To pull back that veil, humanity is mounting unprecedented scientific projects. The Dark Energy Spectroscopic Instrument, desi, in the US is mapping millions of galaxies in 3D to track expansion over time. The European Space Agency launched the Euclid telescope in 2023 to probe the nature of dark energy and dark matter. The James Webb Space Telescope peers into the deep past, gathering faint light from the early universe. Together, these projects aim at one target: uncovering the invisible architect. And here lies the deeper possibility: if dark energy cannot be explained within current physics, then it could be the doorway to entirely new laws of nature. It might push us toward a long-sought theory of everything, uniting the large and the small, the cosmic and the quantum. Dark energy, then, is not just a puzzle, it may be the greatest scientific opportunity of our age. Now, imagine the far future. If dark energy continues its relentless push, the consequences will be staggering. One possibility is the Big Rip. Over billions of years, dark energy could grow so strong that it doesn't just drive galaxies apart, it tears them to shreds. Stars, planets, molecules, even atoms would be ripped apart in the final moments of the universe. Another scenario is the heat death. Expansion never stops. Galaxies drift endlessly away. Stars burn out one by one. Energy thins out, spread across an ever-growing void, until the universe becomes cold, dark, and lifeless, a graveyard of fading particles. Even before these ultimate fates, something eerie will happen. Distant galaxies will accelerate away faster than light, crossing a cosmic horizon and disappearing forever. The observable universe will shrink into a lonely island, leaving only a handful of nearby galaxies visible. For any future civilization living in such an isolated cosmos, the evidence we now see, expansion, cosmic background radiation, galaxies rushing away, would vanish. They might never know their universe had a beginning, never guess it once expanded in a fiery Big Bang. Science itself is tied to cosmic timing. This is sobering, but it is also what makes our present moment extraordinary. Today, we can still see the universe in its fullness, still capture ancient starlight, still test our boldest theories. And humanity has seized that chance. From Euclid to desi to James Webb, from thousands of scientists collaborating across borders, we are witnessing a global drive to understand. Mysteries like dark energy do more than challenge our intellect. They unite us in a common story. The story of seeking truth. Perhaps we will never fully explain dark energy. Perhaps it will always remain partly in shadow. But maybe that is the point. Science is not only about final answers. It is about the pursuit itself. About the shiver you feel when you realize the universe is stranger and grander than you imagined. And it may be precisely these unanswered questions that keep us moving forward. From tiny labs on Earth to telescopes in orbit. From the imagination of a poet to the calculations of a physicist. Whatever the cosmos has in store, whether a big rip, a heat death, or something yet unimagined, human beings will keep watching, keep questioning, keep seeking. Because that is who we are.